the curved mirrors worksheet, and I'll show you how to do a basic lab with a simple curved mirror. The equipment's pretty crude, but it will work. First of all, here's our mirror. It's concave on this side, convex on the other. If I take out the thing, you can see there's a clear focus of the rays there. We want to get it a little bit more quantitatively than that, like actual, get some numbers. So we're going to set you up how to do the lab. And the unit test will involve you demonstrating you can do this in front of me. So all the instructions you will find at the top here. If you care to read them, there's only really 4 things you need to do. Most important thing is you need to center this mirror on the principal axis. And you can do this by measuring its height. And if you go along here, you'll discover the mirror is 6.4 centimeters across. This means 3.2 above and below the axis will work. So I'm going to go here and start at 10, and I'll go to 3.2. It's about there. And then I'll go to 13.2. Picking 10 was nice because it's very easy to go 3.2 on either side. This allows me to place these little horns on the mirror right on my mark. Now the problem is I have the mirror centered vertically, but it could be rotated off axis, and we have to fix that. So to make sure I've got it centered on the axis, use what you know to be true. If I'm centered, this beam that I send in along this black line, along the center axis here, should come right back on itself. And watch, if I rotate this, there's the off-axis beam. So if I turn it this way till it's nice and lined up with my horns, it looks good. Now it's kind of dim to see here. I'll move it over so you can see the line a bit. And if I was off vertically, you'll see this faint line here. Okay? So I'm going to move back till I'm nice and centered. And without this part, you can't do the lab. Now I need to trace the actual profile of the mirror, and this is where my shaky old man hands can get into trouble. I trace the front of the mirror there, and good I haven't moved it. So the first thing we want to do is locate the center. Now, if you paid attention in class, that should be about the focus. Looks to be 1, 2, 3, 4, 5, about almost 6 units in front. So 7, 8, 9, 10, 11, 12. I'm going to take a guess. My center's way out there. And if I'm right, then any beam going through the center comes right back on itself. So if I cross here, the beam is not coming out correctly. If I cross here, hey, the beam's coming out horizontal. That's my focus. So when will this beam here come back on itself? And if I go back here, up I go, look at that, it's coming closer, 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 and then all of a sudden it's going back on itself. So if this is the center, if I've identified it right, watch what happens. You never see the beam at all. It's coming right back on itself. And if I go off this point, like to here, the beam comes back. So to prove to me that you were able to do this, you put a mark here, you put a mark here, and when you're done, you can connect them to show that you knew where the center was. Now what about the focus? To find the focus, I need to go in parallel. And this gets trickier. So I'll come in closer, and I'll follow this line 3 steps up. There it went, and it came out here. Okay? Then I'm going to go below the axis, and I have to try to line it right up on my pencil lines and come in straight. And I'm going to mark it here, mark it there, and put a mark here. Ah, terrible. And a mark here. Now what have I achieved? This is what you got to watch when you're doing this, because you go, oh, it made sense while I was doing it, now what the heck did I just create? Well, if you recall, we went in the center this way, went right back. We went in on the center this way, went right back. Now the focus, remember I went in straight. So here's my straight line going in, like that, and it took off this way, like that. And then this straight line here, like that, took off like this. So this seems to be my focus, F, and this seems to be my center. So this mirror has a focal length of, looks like 3.7 centimeters. But we won't say 3.7 centimeters. We will say 37 millimeters is the focal length. And we use small letter F. So this lens would start a fire 37 millimeters in front of it. So sorry, not lens, mirror, okay? Now if I'm correct, and I did this lab correct, you put the mirror back and you double check you got your center still is correct. Everything's going right back. You put it here, and here's how I can prove you were right. Look how close. There's the actual focus right there. Okay? So it's very close, within 4 millimeters, say, on there. And there's a reason it looks close but isn't quite bang on the mark. And I'll show you here by using a blank sheet of paper. If you take a look, the focus isn't quite a point. It's a bit of an oval. It's actually spread out a little bit. And that's because light is coming in way high, and if you look at this beam of light, there's no way that's parallel. It's spreading. So the ray box is not capable of making a straight, nice parallel lines. And if I drop this in, that's a bit better. And notice now the crossing point is much tighter than before. Watch. See that? You can see the light from the edge is coming in too soon. So you really shouldn't use much more than a tiny little bit of the center of the mirror, and then you get a nice sharp focus. And this is why the mirrors have that carnival distortion around them. I can demonstrate it a bit better here. Actually, I'll do it on this blank page again. If I switch this to multiple slits, like this, you can clearly see now that the high beam here is coming in closer, and the beams that are closer to the center line are focusing further out. And this is called coma. Coma, comma, comet are all the same word. They mean a blurred, stretched shape, sort of oval. Let's go back to our lab here, and I'll follow my beam here that I previously drew on. I'll put the mirror back. There's my focus, and this may be very difficult to see with this lighting, but the beam is crossing right there. And if I move off axis way up here, you'll be able to see in the dark that the beam is no longer crossing at that same point, but you'll have to see that in the dark. The beam starts to misaim really bad. So on any circular mirror that's being used for a purpose other than carnival fun, we would only use a very itty bit of the mirror, or we get a blur. This is also true of your eyes, which is why if you look at your pupil, your eyeball is almost the size of a golf ball, but the pupil opening is a tiny fraction of that. And if your pupil gets really big, like in dim lighting conditions, your vision gets blurry. It literally is blurrier to try to see in the dark. Now I used marker, so I've got a mess on the backside. What you're going to do on the next one is reverse the mirror, and you're going to go this way. And you're going to try to find the center again. just like before, but you'll be moving this beam around, aiming it at a point such that it comes right back on itself, and you will not be able to complete the ray until you remove the mirror at the end of the experiment to show where it was actually going, and that will be the diverging one, and I'll post a separate solution for that.